Thank you very much, Jean-François. You will agree with me if I start speaking French that it's better to use my English than my French for the purpose of this talk. It's a pleasure to be in Paris, as always. I spent some time at Collège de France a long time ago, and I attended Goettingen's lectures in this room, and I have good memories of those times. So I want to talk to you about one class of active matter which is very commonly used to create these particles that essentially lead to the organization that we heard about. So Jean-François talked about self-propelled particles that have an orientation or polarity which comes from motion or self-propulsion. And often when you want to think about mechanisms to build these particles, especially if you want to build them synthetically, you need to think about a non-equilibrium process which will allow you to take advantage of the gradients that are present in the system and essentially turn them into movement by coupling to the fluid flow. And I will be talking about this kind of process a little bit. So generally speaking, suppose you want to start from the small scale and think about colloidal particles that we know about. We know that they undergo Brownian motion. It's interesting that people thought initially that because small particles undergo Brownian motion, that must be a manifestation of life, and then later on, so Brown showed us that that is not the case. And it's possible that many other things that are known to be manifestations of life, even today, are also like that. So if you actually look at them, you will realize that there are very good and simple physical reasons behind what they're doing and what they're exhibiting. And then one possible way to justify what we do could be that we will sort out all those things that are not manifestations of life and then leave the biologists to understand what is manifestation of life in reality. These interfacial transport mechanisms that I call phoretic mechanisms are typically the result of interaction between a thermodynamic potential which has a gradient and some sort of boundary which basically imposes a constraint on them. If you think about, for example, this case, diffusiophoresis, which is the case where you have a gradient in the chemical potential of some solute particles, then if you have just a solution with a gradient in it and nothing else, that solution will achieve a stationary condition. But if you have introduced additional particles with surfaces like colloids, then the interaction between the solute molecules and the surface will lead to relative motion of the fluid velocity of the fluid, and that will lead to a velocity which is going to manifest itself in the motion of the colloid. So we can work that out essentially by looking at conservation of the number of solute molecules in the solution with a concentration C and a flux which comes from the diffusion part, Fick's law, from the drift part, which has in it the interaction between the particles, the solute molecules, and the surface of the colloid, advection by the fluid. And then the Stokes equation, which essentially is conservation of momentum. It has in it hydrostatic pressure and a body force, which again will come from the interaction between the solute molecule and the surface. And if you solve these equations together and introduce the incompressibility, you can somehow find a condition between them which will tell you that while near the surface of the so essentially this quantity, which is a combination of what you can call hydrostatic pressure and osmotic pressure, will have to be a smooth function, satisfy Laplace equation if you ignore advection at so-called low Peclet number conditions. And then you can see that layer by layer, this combination of the two pressures, if you want to call it that, will need to be constant very close to the surface, where the interaction between the solute molecules and the surface is very singular. So you're talking about something like van der Waals interaction, which is a very strong power law, or exclude volume effect, which could even diverge at the surface. And that means if you have out here where the interaction is not working, a situation where the hydrostatic pressure is constant, but the solute concentration has a gradient, then when you get close to the surface and you modify that, for example, in the extreme case of excluded volume, you expect no particles on the surface, then the gradient on this combination will have to be taken over by the hydrostatic pressure. And that means there's a layer here very close to the surface where the solute molecules interact with the surface, where actually there is hydrostatic pressure, even if there is no hydrostatic pressure outside of that layer or imposed globally onto the system. And that hydrostatic pressure will basically move the fluid as always, and will lead to a relative slip between the colloid surface and the fluid in its rest frame. If you're not interested in this length scale, which is a few angstroms, so to speak, then you can basically just ignore all this microscopic detail and say that when there is a gradient in the concentration of the solute, there is a relative slip between the fluid velocity and the colloid surface. And you can calculate that relative slip velocity. The mechanism that I described is force-free, and because of that, you can use it to make self-propelled particles. All you need to do is somehow induce this gradient that I mentioned locally without the need of an external implementation of that. And you can then call this phenomenon self-diffuse geophoresis. For example, if you have a Janus particle which has catalytic parts that are asymmetric, let's say half of it is coated by a catalyst, and you put that in a solution of a molecule with uniform concentration, which is the reactant to that catalytic reaction, then the catalyst will do its work over time and produce more product molecules on one side and deplete the reactants on the same side. So you will have a gradient in the reactant, which is in this direction, and a gradient in the products, which is to the right. And the combination of these two gradients and the interaction with the surface would give you essentially always a non-zero, unless you tune it exactly such that it will vanish, a non-zero slip velocity, which could be in any direction depending on the interactions and so on. And then the result of that will give you propulsion in some direction. The advantage of this mechanism is that basically you have something like an engine on the colloid. You don't have to do anything other than provide with the uniform concentration this fuel, which is now going to create the non-equilibrium situation. And then the particle will generate the gradient wherever it goes. So to analyze this motion on the scale that I described, coarse-grained and not at the molecular scale, you essentially need two parameters. One of them is this Onsager coefficient mu, which is basically, it's called mobility. It basically tells you what slip velocity you get for a given tangential or transverse gradient in the concentration. And the other one, which I call activity, is essentially the rate of catalytic flux or introduction of additional solute molecules into the system. So this could be the rate of consumption of the reactant and the rate of release of the products. Essentially, both of these parameters, mobility and activity, could be both positive or negative, depending on how you essentially set up this system. This parameter alpha tells you how far away from equilibrium you are, because it's the rate of non-equilibrium activity, whereas this one is just a linear response function if you want. Then you can set up any type of geometry or any type of pattern for the mobility, for the activity, and study what kind of symmetry breaking you need to have so that you will have self-propulsion. And you can study other types of thermodynamic potential, not just chemical potential, but also temperature or electrostatic potential, and so on. So if you do this in practice, it works. This is a polystyrene bead which is coated with platinum, and it's moving like basically a living system like E. coli. You can analyze it systematically from the trajectories through the mean square displacement as a function of time, and from this curvature you can extract the velocity, which shows something like a Michaelis-Menten dependence on the fuel of this catalytic reaction. So that's basically an interesting way to learn about the reaction that is happening on the surface from just doing microscopy, so particle tracking, if you want. It turns out that this particular system, platinum-coated polystyrene bead, which has been produced by this method of vapor deposition because of the thickness gradient that it has, breaks the symmetry in more than just back to front way, and it couples hydrodynamically to the surface, which means that for every surface that you have, essentially you quench one of the directions of orientation. And if you have two of them, you can completely confine it into a linear motion. Even if it's opposing another one which is trying to push, it will basically stop there and wrestle with the particle which is in its way. So you can actually guide these particles by just having geometric features on the surface without having to have any specific contact like molecular motors do, which basically need to bind and unbind constantly, or having something like a magnetic field which you externally impose, because that would interfere with essentially whatever else is in the system. So if you have a magnetic field, every particle in the system will just do the same thing. But this way you can have a situation where the particles do different things. Then you can study how these particles will behave essentially stochastically, and it turns out that depending on the symmetry of, let's say, the coating or the polarity of the particle, you can have different situations for the mean square displacement. Essentially, the system will have a number of time scales. This is the rotational diffusion time. This is the diffusion time of the solute around the colloid, and this is the crossover time between inertial and viscous regime. And you will have different exponents. For example, in this case, you can have an interesting anomalous diffusion case with an exact exponent 3/2 for a particle which is fully coated with the catalyst, but basically you can have density fluctuations in the distribution of these solute molecules around it, and because of that you will have local, instantaneous asymmetries which will propel the particle but will be forgotten very quickly at this time scale, and because of that you get this less than propulsive motion. Now, there is a very interesting structure in the way this system goes away from equilibrium, which you won't see when you're looking at just one particle. As soon as you start looking at two of them, then you realize this interesting feature. So suppose I have two uniformly coated, so apolar particles that I bring to interacting range. And then if you think about it, this particle, which has been prepared independently with its own activity and its own mobility, will produce a chemical field which decays as 1/r and is proportional to alpha, which is the activity coefficient. And then the other one will respond to the gradient of that by its own mobility. So in a way, this is a dissipative version of an electrostatic interaction or a gravitational interaction where mu and alpha are playing the roles of the charge or the mass. However, if you think about these two different objects, each of them will react to the field which is generated by the other one with its own mu. So the velocity of this one is proportional to alpha 1 mu 2. Velocity of this one is proportional to alpha 2 mu 1. So unless I actually tune these parameters so that the product of alpha 2 and mu 1 is the same as alpha 1 and mu 2, which is probably very difficult to do experimentally, then the action and reaction symmetry will break, which means in general the interaction between these two systems cannot be just explained by one statement. You cannot just say these two attract each other or repel each other. You have to say what A feels towards B and what B feels towards A. A bit like relationships, you know, we don't talk about two people with the same statement, with a scalar quantity. You have to say what A is thinking about B and what B is thinking about A. And it could be that they don't think the same thing, and that creates frustration, which you will see in the next simulation. It's very easy to see this kind of thing by just setting the valences, if you want, to values that do not exactly match in terms of neutrality conditions. So here you can have these so-called molecules, both in the form of AB and AB2, A being the red one and B being the blue one. So neither of these, if you look at the valences, actually neutralize the system in terms of the rate of activity. So AB3 would be the right one to give you a neutral molecule if you think about ionic molecules. But happens to be that these two molecules are both stable and they can exchange particles. And you can basically sweep the parameter range and observe different kinds of molecules, which will select relatively stable structures, and because of the symmetry of that structure, will exhibit some form of activity. For example, these ones will all have an axial symmetry, which means they will have propulsion along that axis with some velocity. These ones don't have that kind of symmetry, and they will spin around themselves. And these ones are too symmetric to show any mechanical activity. And essentially, what you have here is a Lego version of a principle which we find in proteins, and that is essentially having these building blocks which are different from each other, and we can tune them and their interactions with one another such that they will find each other in the solution, form structures that are relatively well-defined in terms of geometry, and then that well-defined geometry will define their function. In this case, it's propulsion and spin and so on. You can also have a situation where the function is dynamic. For example, this molecule AB3 can exist in some parameter range between two different states, both stably with a little barrier between them, which can be overcome if you tune the parameters right, can be overcome by thermal fluctuations, and then the system can just switch between these two isomers. Now, if you look at the symmetries, this one is too symmetric to show any activity. That one is self-propelled, so you have a situation where you switch between run and tumble in this system without doing anything. You just leave these colloids in the solution, they find each other, and they demonstrate this type of bi-stability. You can have more complex dynamic structures. For example, here you would see if you wait long enough, a big molecule which is going to form when this particular last monomer is taken up, which is very symmetric, so it cannot actually propel, but it has a bifurcation to an oscillating state, and it picks up a frequency which can be tuned by these parameters, and that would basically be its stationary or long time state. So far I talked about a particular regime in the parameter space of these mixtures, where essentially the stationary state, the uniform state is stable, and essentially the stationary state is uniform with some small-scale molecules that form. But it's possible to go to other parts of the parameter space, and in fact it's possible to think about mixtures in general and ask this question: what happens when you create these colloids and just mix them together? What kind of different phase behaviors you can get? Turns out that you can study this using linear stability analysis relatively easily for the most general case of M species with mobilities mu I and activities alpha I. If you just mix them together, you can write down equations, so conservation laws for the concentrations of each species, and then an equation for the diffusion reaction of the chemical, which they all basically produce or consume. This is a simplified version of the model, the more complicated model in which there will be different kinds of chemicals involved as well as different types of colloids. And then you can essentially expand around this homogeneous uniform solution and expand for the concentration also. And then if you look at the stationary state, you would find that by using basic analysis of the modes, you would find that m-1 of the eigenvalues of the matrix that you find from this dynamics are going to be essentially diffusive, and there is one mode which is essentially diffusive with this added constant, and this is a basically linear combination of the products of mu's and alphas and the initial densities of these particles, and then you can tune this combination such that you will change the sign and create an eigenvalue which is positive and create an instability already for the smallest wave vector of the system, and then that means the system will undergo phase separation. Not only you can find the condition for this instability, but you can actually solve for the eigenvector corresponding to that eigenvalue, and that gives you the stoichiometry of the different components when they join together to form this unstable mode. And as you can see here, the stoichiometry is determined by the ratios of the mobility. So essentially what this tells you is you can tune the system such that it becomes unstable and it forms clusters with very well defined ratios between different types of the species. And you can do this for different signs of the coefficients, so producers and consumers and so on. I show you quickly some sample phase diagrams. So if you have the situation where you have a producer for two species, so alpha 1 is positive, and a consumer alpha 2 is negative, it turns out that you can have basically 4 different possibilities. And these are interesting to look at. For example, this corner in this diagram, which is mu, alpha, and rho, with the sign of the mu chosen. Well, sign of alpha is chosen first, and then sign of the mu's are changing. We'll have these different combinations. For example, in this corner, 1 is attracted to 1, 2 is attracted to 2, and 1 and 2 repel each other. And this is essentially the inverted gravity. So it's essentially similar particles attracting and opposite particles repelling. It's gravity with negative mass. Down here you have opposites attracting and similar particles repelling. That's electrostatic. And then here you have a situation where similar particles, well, 1 repels 1, 2 attracts 2, and then 1 is attracted to 2, and 2 is repelled by 1. So this is an asymmetric situation, and down here you have the opposite case. And in these corners you have phase separation into a dense cluster which coexists with a dilute cluster, and the dense cluster is essentially of a given stoichiometry, so the mixture is controlled by the ratio between the parameters. And in this corner you have a phase separation between 2 dense phases, essentially being predominantly dense in one species. And down here you have the situation that I showed you earlier. So these molecules that form with an overall sort of global uniform system. Here you can see an example of this corner simulation, which is done by Jaime Agudo, my postdoc, in 3 dimensions. You can see that the cluster essentially picks up red and blue and mixes them, and essentially if you count, you will find that the number of reds and blues are according to the stoichiometry that is selected by the linear stability initially, but then eventually it settles into another ratio which is now controlled by the rates of activity only. This is another phase diagram where you have 2 producers, so positive alpha 1 and positive alpha 2. And you can see that you have a situation where everything collapses, the system is homogeneous, without molecules. You have phase separation between a dense phase and the alternative, the opposite dilute phase, and a depletion layer in between them, which is basically very different from what you have in the previous case. And you get different kinds of, so this is an example of the depletion zone that I told you about. This is an example of the phase separation between the 2 phases, etc. It's possible that one can push this electrostatic analogy a bit further, and here I have some slides on essentially temperature or thermal energy being the thermodynamic potential. In fact, this has also been looked at experimentally in the group of Masaki Sano, using basically the same geometry, the Janus particle with the metal coating, but then using the metal to create heat locally in an asymmetric way. And when you basically go through, I think I will go through these slides quickly, go through the formalism with essentially a drift term which comes from the gradient, and you set the flux to 0, and you couple that to the heat conduction equation, which in stationary state would look like a Poisson equation. Essentially, you can show that the system will satisfy a generalized Poisson-Boltzmann equation. So this would be very similar to what we know of ionic liquids at room temperature. But then, depending on the sign of the interaction, this exponential will be positive or negative, and then the situation could be stable or unstable. So we have generalized Debye lengths and generalized Birum lengths, essentially coming from the same analogy, and we can have something like a counter-ion condensation happening and something like a collapsed transition, or first a stable configuration which looks like a star because you have a dense, you have a dilute system which creates heat, but stays at a basically relatively dense gas structure with a well-defined radius, and then it gets rid of the heat from the boundary. And then if you increase the coupling constant, you see an instability which looks like the collapse of that structure into what you can call a colloidal supernova. Essentially, it's the same kind of instability. The role of gravitation here is switched with these phoretic interaction, but the rest is very similar. You can also have swarming of these colloids. For example, if you don't break the symmetry at the level of the colloids, but you guide them from one side by shining some light, you will create a swarm because of the attractive interaction, which selects a well-defined size. And then there will be fluctuations around that. If you have polar particles, that's more complicated because essentially you now have a number of ways to couple the gradient of concentration to essentially the activity of the particle. So before it was just attraction or repulsion, the translational motion, and that mode still exists. But if you have polarity, you can have this alignment interaction. So you can have an angular velocity which comes from the orientation of the colloid and the gradient, and that will create a situation where the colloid will align with the gradient and then swim towards it, let's say, or swim away from it. You can have a situation where the local value of the reactant or fuel will determine the local velocity, and then it will go away from that region to regions where the fuel is smaller, and that is similar to what we know in bacterial system. And it could also be that we have this coupling between the gradient and the translational velocity, where the motion happens instantaneously along the direction of the chosen direction of the colloid itself, but then over time it drifts towards the higher concentration or away from it. And then all these so-called channels, if you want, of coupling between gradient of concentration and the colloidal particle will basically play with each other and create a situation where you can tune the parameters by changing these things and go from one type of behavior to another. Essentially, you can write down a many-body dynamics for this system and work out stability diagrams like these, where you essentially find different modes that are unstable. So you can have spontaneous oscillations. Similar to the molecule that I showed you, you can have asters forming or bands forming, so essentially a finite wave vector instability in the concentration, or a collapse like the gravitational one, and so on. So I basically have chosen a few very short sections also on other types of interaction between chemicals and motility that are present in active matter. One of them is the bacteria on surfaces. This is essentially a singular limit of chemotaxis, where bacteria like Pseudomonas, they move on the surface and essentially leave behind some sticky polymeric material, and one wonders why that is, because it's a very expensive thing for the bacteria to create these polymers, mostly sugar, polysaccharides, and they are basically what they can easily use and live on, but they choose to just leave them behind, and they rarely diffuse at the time scale that the bacteria move around. And you can sort of do the maths to think that it's very easy in 2 dimensions for 2 of these trajectories to cross each other. In 3 dimensions, it would have been much more difficult, but then essentially they cross each other very quickly and find a way to aggregate and start a social lifestyle, which is basically the onset of biofilm formation. So you can learn things from basically writing microscopic equations like the ones that we wrote for colloids. And one of them, in the case that you have a polysaccharide trail like that, which is left behind by a previous bacterium, is that the gradient sensing cannot be simply in the form of translation, which is what we know from bacteria, because basically there's only one type of gradient in this track, and that's perpendicular to the track. If you think about the profile, it has to be, because it's released essentially in the center, it has to be that it has a cross-section which has gradients on both sides. And then as you go along, essentially the gradient is a lot weaker. If you just want to have a particle which orientationally doesn't do anything and choose its component of velocity, which is along this path, stochastically to follow a path, basically you don't get a very efficient mechanism for trail following. But if you have this alignment interaction, which I discussed, so something like the orientation cross the gradient, and now the gradient being perpendicular, it turns out that you would create this oscillatory type trajectory, which basically is a much more efficient way of following the track, because as soon as the bacterium is outside, it will realize and it will correct itself, even if it's subject to thermal fluctuations. And it turns out that, well, you can write down similar equations and in fact calculate all these parameters from a microscopic model, which you can fit to the experiment, and it turns out that this mechanism works quite well when you look at least for the case of Pseudomonas, which was done in the group of Gerald Wang. They can change the rate of polysaccharide release, and then for different rates of release, they can study the individual trajectories, and also with orientation and position, and also the self-organization pattern. And basically this mapping will teach us things, for example, about the way I'll probably skip this part, it's a lot of detail, but basically you have many, if you calculate these things, you have many components that all depend on the concentration. For example, your biologist colleague might ask you, okay, suppose the bacterium is now releasing the polysaccharide, and suppose the force that is essentially pulling the bacterium is sensitive to that, because the pili are, and it gets stronger, but also the viscosity goes up because of the presence of the polysaccharide, and then maybe the rate of attachment detachment also changes. So what happens when you put all of those things together? And it's impossible to predict theoretically whether the velocity goes up or down, because you have the force here, the friction coefficient there, and the rate of attachment and detachment there, and all are arbitrary functions of the concentration. And then when you measure the actual trend experimentally, you can somehow and you do that for various independent parameters, for example, rotational diffusion and velocity in this case. You can use the microscopic model, which will limit the number of independent parameters that you have. and in fact learn something about how these individual parameters depend on the rate of or concentration of this polysaccharide. Okay, so I want to talk briefly also about enzymes. Of course, you know what they are. They basically they are drivers of non-equilibrium activity in biological systems in a very specific way. So typically what an enzyme does is it interferes with a chemical reaction which is essentially going to happen, so that in this diagram the particle going from this minimum to that minimum, or the state of the system, would represent this chemical reaction of substrate S going to product P. So substrate here is using the language of biochemists. But there is a big barrier in between, and this will happen over a very long period. And when the enzyme comes along, it will somehow modify the shape of that substrate molecule, and the binding will facilitate the opening of the bonds and so on, and somehow the release of the product is facilitated. So it's equivalent to saying that the barrier between these two states is lowered, and therefore this transition happens much more efficiently. And the good thing about enzymes is when you have a specific, at a specific place, at a specific time, an enzyme, it means that you can drive the system away from equilibrium at that point, at that time, and then when it goes away, you're back to equilibrium at that point. So this is nature's way of programming what it wants to do, and basically it's very interesting to study their behavior in a statistical sense. So in recent years there have been a number of experimental observations and experimental reports essentially reporting two things. One is enhanced diffusion for enzymes when they are catalytically active. So somehow the diffusion coefficient changes, it increases, and it increases by a few percent or a few tens of percent, not by 10 to the minus 5 or 10 to the 5. So order of magnitude doesn't change, and somehow this seems to be the case for molecular catalysts, angstrom level to enzymes, to nanometers, and also to larger ones. So there seems to be, and also it doesn't seem to be too sensitive to the rate of reaction, although there's not consistency on that. Also, there are reports of chemotaxis, and this might sound confusing because for E. coli, when we talk about chemotaxis, we know that there are receptors that measure the concentration of the chemicals, and then they feed back that concentration as a function of time to the action of the motility machinery, to the molecular motor, and there is none of that here. It's just a drift, if you want, which happens because of this gradient, but that term somehow has been used in the literature to explain it. Essentially, it's the same as the phoretic drift that I mentioned. I didn't want to talk about the enhanced diffusion part here, but the phoretic part, or response to the gradient, which is chemotaxis, seems to be quite relevant to what we discussed so far. There are several reports, and in fact there are some reports, so most of them, they essentially suggest that enzymes go towards the higher concentration of their substrates, and in this particular case of ureas, there seems to be, there are two reports in the literature that are in contradiction with one another. And basically we want to understand what is happening with the enzyme. So do we have a universal tendency for the enzymes to respond to gradients, and can we understand it in any way, or can we understand these two conflicting observations? Essentially, it's possible to describe the stochastic dynamics of enzymes. All we need to do is worry about basically the processes that they're involved. So they form a complex with this molecule. There is binding, unbinding going on, and then there's essentially there are rates for that, and then there is a gradient of the substrate concentration, which means if you think about it, the balance of this binding-unbinding process is being modified in different places in space, because essentially at every given point there is a different concentration. And then there's also hydrodynamics and non-specific interactions as well, which will lead to the phoretic type of interaction that I discussed so far. And we want to know what happens when you put all of these together, whether you can basically describe what is happening to this system. So you will be able to write for the two population of free and complex enzymes, reaction, diffusion, drift type equations. So you would have the diffusion part, which now basically has different diffusion coefficients for whatever reason that they might come by. And then we have these drift terms, and then we have the binding and unbinding, which essentially will take the system from this population to the other one and vice versa. And then we can look at all these individual terms. For example, the drift velocities we can all calculate through the diffusiophoresis of individual enzymes towards their substrates or the molecules that are available in the solution. Essentially for the total concentration of enzyme, which is the sum of the bound and free enzyme, we can come up with an effective drift diffusion equation. That is basically the same way that we look at, let's say, flashing ratchets. If you have ever tried to teach ratchets, it's really not easy. And we have Jacques to blame for that. But you can talk about the concept, but the calculation is quite subtle, and basically it will be something similar to that calculation. We can use the separation of time scale and describe this motion at the time scale where the binding-unbinding has equilibrated, and in that scale for the total concentration we can calculate effective parameters, effective diffusion coefficient, effective drift velocities that all depend on these concentrations now. And basically putting them all together, we can find, let me just summarize this in this graph, we can find for the response to the gradient two different mechanisms that will compete with each other. One of them is essentially a phoretic mechanism, so the enzyme tends to go towards the higher concentration of its substrate, because essentially the interaction between the enzyme and the substrate must be predominantly attractive. Otherwise, it will not find it in the solution to go in that direction. And the other one comes from essentially this dependence of the effective diffusion coefficient on the concentration of the substrate, which is basically also a consequence of this two-state model. And that has a coefficient, if you take the gradient, that depends on the concentration, which means when these two are competing with each other, it matters whether you are at low concentrations of the substrate or at high concentrations of the substrate. At high concentrations, you expect phoresis to win, and at low concentrations, you might expect for this enhanced diffusion component to win. And this corresponds to the case of the two concentrations that have been used in the experiment. So one of them was very low and the other one was very high. I want to finish by a calculation which connects to what we heard from Jean-François, because he talked about giant number fluctuations and hyperuniformity towards the end of his talk. So basically, I want to talk about a model in which you can imagine living populations like cells that interact with each other chemically via chemotaxis and also grow and divide, have a population which undergoes stochastic dynamics, and you want to ask whether it's possible to have a homeostatic condition, essentially in the language of phase transitions, to have some form of stability which will basically switch between two different phases using continuum type descriptions. And essentially the idea is we have all these independent stochastic components, and they interact with each other somehow, and then we have these tissues or organisms coming out of it. Somehow, somewhere, there has to be a mechanism where they can find a way to collectively regulate what they do and essentially come up with a collective stable phase, which speaks for all of the individual local activities. And that is, in the language of phase transitions, essentially finding a way to, let's say, break the symmetry and have phase transitions. In the model that we looked at with Anatoly Gelimson, my former PhD student, we incorporated these chemical interactions, so exactly like I described, a response to the gradient of the chemical, which is being produced or consumed by all of the particles, and then we also introduced cell division. So every particle might split into two, or every one of them might die, and on top of that, we added equilibrium noise that comes from essentially diffusion, and non-equilibrium noise, which comes from number fluctuation in a system that doesn't have a conserved number of the total number of particles. If you add all of these together, so this coefficient mu here is the chemotactic response, and chemical phi is produced or consumed by this population of the cells, and you have these processes for the dynamics, you will find out that essentially the system, as a function of this mu parameter, has a critical point which is not at zero like in the case of normal chemotaxis. So when you couple chemotaxis with cell division, the critical point is shifted to a non-zero value, which means you will need to have essentially chemoattraction between different cells to maintain the system, which is dividing, let's say, at a stationary state. And then when you look at the fluctuations on top of that, you will have two terms in this effective equation for the density fluctuations. So rho here is the delta rho that we heard about. And these two terms are essentially the same in power counting. They're both proportional to second power of the density, but this one is conserved. It's a divergence of the gradient of a solution to a Poisson equation. So if you count the number of del operators, you have two here at the top and two here at the bottom. This is the Green's function representation. So this one will turn out to be rho squared as well. But if you integrate this term over the whole volume of the system, you get a boundary term, or zero, when there's no boundaries. And if you integrate this one, you don't get zero. So it means that symmetry-wise, these two terms are not the same. And that allows them to compete with each other. So the cell division or growth term will compete with the chemotactic term. And that competition, if you use dynamical renormalization group and calculate essentially the flow of these parameters up to one loop, so the lowest that you can do for this system, you will find out that there is a fixed point in the space of the chemical interaction and the growth and death term or rate, which essentially has a basin of attraction which is not infinite. It's bounded by this separatrix, and then beyond that dashed line, you basically flow into another fixed point, which is a strong coupling fixed point. So essentially, and also in terms of the noise terms, there is a stable fixed point in the cross-section that we have. And this is all happening at the critical point. So what this tells us is if you start from a microscopic set of parameters that belong to this region, the system will essentially come to this fixed point in which the chemical signaling strength will somehow balance the strength of the growth and death, and essentially the population will come to a stationary or homeostatic condition in which everything is constantly renewing and there is constant interaction between them, but they are basically staying the same. And if you cross this line, you go there, essentially the growth and death term grows out of control in the sense that no chemical interaction strength can control the fluctuation. So it will essentially go to a place where nu2 is much stronger than nu1 and is not going to be sensitive to nu1 anymore. And that's a case where we can say the chemical interactions can no longer regulate the growth and death term. If you look at the exponents for the mean square displacement, you can find an exponent for the degree of diffusion or degree of superdiffusivity. That's called alpha. And you can see that alpha is, for example, 1.72 in 2 dimensions, or just above 1 in 3 dimensions. That basically shows that the motion is super diffusive. So it's regulated and stable, but also things move around very efficiently. You can also measure this exponent beta, which gives you the rate of number fluctuations. And I don't have a slide in terms of delta n as a function of n, but I have it as a function of L. And you, having seen this calculation with Jean-François, you can clearly tell that this beta, when you divide it by d, essentially it gives you that giant number fluctuation or number fluctuation exponent. And it turns out that what you get is lower than 1/2. So the system is hyper-uniform. And that's quite interesting. It's not something that is put into the model in any way. And it's not something that I particularly expected, but it basically tells us that when you have these chemical interactions and cell division in the system, somehow the overall number fluctuation in the system is regulated as well, which means the size of the population is also controlled, better than Poisson's statistics. And why that is interesting to find out. Okay, so with that, I think I can conclude. Essentially, I showed you a very sort of wide variety of different systems that interact with each other via these gradients. Essentially, they all have long-range interactions. And because of the long-range interactions, they show very interesting non-equilibrium effects. It turns out that many of the experimental systems that are used to create self-propulsion and so realizations of active matter fall into this category, which means that many of the, for example, when you think about formation of clusters in the experiment, which are observed very often, I would put them in the category of the collapse transition that you get from this kind of model, rather than the type of thing that you see, for example, from short-range interactions with persistence in their orientation, which is known as motility-induced phase separation. So I think I can stop here, and I'll be happy to answer any questions.